discussed, may I have your attention? Before the coffee break, we discussed the dirty evaporation pan. I hope I didn't say something wrong. When the water is dirty, it's darker, so more absorption of energy instead of reflection. Therefore, more heating up of the water, more energy available to evaporate. So you have more evaporation probably out of a dirty water compared to a crystal clear water. Now, so with the dirty water, you overestimate the evaporation because you evaporate more than you would have with crystal clear water. If I made a mistake, my apologies. A gentleman just told me, but maybe I wasn't clear. Good. Now the lysimeter. How do we calculate evaporation out of this? The input to a lysimeter is the precipitation. I think you agree with that. The output is the evaporation. With the water balance approach, we need to get input and output, and then also we need how much water is leaving the system. Yeah, so that's the leaving in that direction in our case. So you need to actually really calculate the water balance equation. We have that here. The evaporation, the real ET then, ET because it could be transpiration and evaporation, is the precipitation minus the percolation, the water percolating down to the groundwater, not being accessible for evaporation anymore. Yeah. And then the change in the soil water storage. Of course, some water can be stored there. It's a DSTT, and then you can calculate that. These simple equations are beautiful for an easy equation for an easy question in exams also. So here I have an example. You couldn't get a simple little assignment like this, and then you calculate it, and it's very straightforward. I don't want to go into details of these simple calculations. Now let's look at some reality. How do we measure evaporation? Was it too fast? Oh, am I too fast? All my slides, of course, are on Moodle, and the original PowerPoint you find on SUH. You know, I'm opening the PowerPoints when I'm here. By the way, wanted to tell you anyway. In my public, yeah, my abbreviation is SUH, Stefan Uhlenbrock. Oh. SUH/public. There you find all the PowerPoint slides, which I show if you need the original PowerPoint slide. Huh? The PDFs you have in Moodle anyway. I think some of you printed them also out. You have to think if that is worth to cut the trees and to kind of print all my slides. It depends on what kind of learner you are. You know, some of you need printouts, some of you study on screens. I leave that to you. Yeah, but we did not print it for everybody because we felt it's too much paper. And if we flood you with paper, there's a danger that people don't read anymore. Yeah? So rather less, and then make sure that they read this. Okay, this is the example again. You can study this little equation, I think, at home. Let's look at some pictures about measuring evaporation. I said the first thing to measure evaporation is with micrometeorological measurements, where we measure the rainfall. You see rain gauge here. We also have rain gauges in different elevations. You have energy balance measurements in different elevations. And you also have wind speed measurements in three-dimensional space, so kind of showing the direction and the speed. And with this change of humidity and wind speed changes, you can really calculate the vertical fluxes of latent heat, and then you can calculate evaporation. These towers, Met towers, have anybody been on one of these before? None? I've never seen it? Well, they exist in many countries, and it's quite scary. So I'm not very good with height. So if you walk up there, I was always on my knees after already half of the height because it's so shaky. You know, it's a nightmare. So I decided to become professor, not a technician who is babysitting this instrument. You're laughing. You know, if you go up there because they're really the wind is moving them back and forth. Of course, they are fixed. They told me. Yeah, these are these lines to stabilize them, but they were shaky, and I don't know. Not something for after the breakfast to do. Some other pictures, some other towers. You see all sorts of different examples where people measure in detail meteorological measurements. And most important is, of course, to do that also above the canopy. Yeah, you need measurements above the canopy because there you have only the evaporation from the canopy. Yeah. But doing one of the excursions, you should really climb one up. In Holland, we have one Met tower, which I think is 150 meters high. It's near Utrecht. And some excursions go there also to visit that. It's amazing, 150 meters to measure different meteorological parameters and different elevations, and also quality of air and precipitation, etc. Yes, please. Yeah. Out of the rain gauge, the evaporation, or?
No, yeah, because I know a rain gauge, I don't think you can put that high.
But
What about evaporation?
yeah, well, they measure energy balance parameters here in different elevations, but they also measure the rainfall up here, yeah? Really above the canopy, yeah? Before any disturbance of vegetation. That this is very much exposed to wind, and that you have a bit of problems with accuracy, I agree, yeah? We discussed challenges of rainfall measurements in the last lectures, but they also measure rainfall, yes, yeah. And they are also sometimes here, and then they have different arms going out to measure rainfall again at different elevations, yeah, different heights. Yeah. But it's a challenge, yeah. Yeah. Good, and I hope that you all will visit one of these things, and maybe you have similar experiences like I had. Now, Thufo, the gentleman asked me already before the break, how do we measure that? I said if we would measure with different rain gauges here below the canopy of this nice plastic plant, it depends on where you put the rain gauge. Right? Everywhere it's different. To account for that, what people do, they measure in these kind of Thufo gauges. These are long pipes, open pipes, you see it here, yeah, and they collect all the water falling into these open pipes and then send it down to a measurement device where they measure the volume of rain. The challenge is to keep these things clean. There are always needles, dirts, bird shit and whatever in these, and then they clog, and then you cannot measure properly anymore. Huh? But you see here different these Thufo gauges up here in the forest where they really beneath the canopy try to measure Thufo. That's how they do it. Clear? Why is it so important to have them as long as possible? The longer, the more representative they are, of course. If you're very short, you still have the same problem. But if you have several meters, then you say, well, you cut through different circumstances there beneath the tree canopy. Here you see these are different type of collars around the tree to measure the stem flow. Stem flow, again, is the water rinsing down here at the bark here, at the outer side of the stem, down here. And to collect that before it enters the ground, you put these collars around this. You see a bit better on the next gauge, next picture at the next page. Oh, it's difficult, yeah. And then you can measure also the stem flow. Yeah, maybe you see that here. Didn't I have a better stem flow picture? Here you see this nice stem flow. This is a collar, and the water rinsing down here goes into this plastic tube, going into here, going into this tank, and then you can measure the stem flow. Yeah. Now, another way of measuring the throughfall in a tropical forest, you see here, these are all little rain gauges put on a net, yeah, and these always, they have a funnel, and they always collect water, and they were measuring then with many smaller rain gauges a pattern of rainfall beneath the trees. It's quite interesting because you have then really different patterns of rainfall beneath that canopy. Yeah, so you can do some geostatistics of it, and it's very interesting. Yeah, nice work. They also looked at the quality of the water then, and different between trees or just below one trees, how the quality differs, and how that then influenced different ecological processes at the ground. This is another experiment where they were interested to really eliminate the evaporation from the soil. Yeah, so they completely covered, made that waterproof here, and completely covered that you don't have any through-fall or stem flow going into the soil here, yeah, and really cut the trees off from direct rainfall, through-fall, and stem flow. Yeah. They even let trees die, you know. Poor tree has to die for the science, yeah, but yeah. Somebody has to bring in here something, and then they were studying then the behavior of the trees. They put them also under moisture stress. You can imagine that the tree here in the middle, who doesn't have any access to surrounding lateral inflow, then really dries out quickly. And then how the trees behave, what kind of moisture stress compensation measures the trees do, and so that's what they were studying. See the same thing in the winter. And yeah, they were really studying in detail what happens on the surface here. The measurement of stem flow we looked at already. Other measurements of stem flow, these are these different colors. Yeah, also here, where people really try to measure that pretty accurately. But I said before, it's a headache to do, and it's to do that accurately is really a challenge. I need a lot of maintenance and looking after it. Okay, this was something on measurement. Any question on measurement before I go to estimation of it with some formula? Not yet. On what does the evaporation depend? What did we discuss so far? Think of a forest. On what does the evaporation depend? Tell me the parameters. Radiation, yes. Wind. Moisture, where? In the soil and in the area here, so the humidity and the soil moisture, yeah. Other things? The canopy, the structure, the geometry, yeah. Leaves, yes or no, yeah. Or what? Yeah, the precipitation, very good. Yeah. Energy we said already, huh? Temperature, of course, is an expression of energy. Yeah, did we forget something? No, I don't think so. Let's look at this. We said energy or net radiation, the humidity, the temperature, the wind speed, and the soil water status. But also on vegetation characteristics. Therefore, I made it green, like the height, the canopy, the roughness of the vegetation, roughness because of making turbulence to the wind field. And also the species. Young, fast-growing species are transpiring much more. Fast-growing means they take on a lot of carbon, and therefore they lose a lot of water via transpiration, while old trees that do not grow that quickly anymore, they also have a lower loss of water at the stomata. So the age of the trees and then the growing characteristics also impact evaporation. There are a couple of examples. I don't want to go to all of them. It's a bit boring if I kind of do this here, but in every textbook, like the one you have on the website from Dr. Laat, you find quite a number of different formulas with different parameters. They all try to estimate evaporation in a simplified way. Usually you don't have measurements for all these parameters. Yeah, would be nice if we would have perfect measurements for all this everywhere, but usually we don't. Therefore, people were looking at some simplified equation, for instance, using only temperature, or using only humidity, or using temperature and humidity. These are two terms that are a bit easier to measure, yeah. And then you have different formula to do that. Like the method of Thornthwaite estimates the potential evaporation over grass, and it uses the temperature. I think even at 1400 hours, we have to look that up, and the heat index, where there are tables for. The Blenley and Criddle method uses the temperature, the day length, the crop, and some geographical coefficients, which are all in different tables of different textbooks. Jensen and Heise method uses then other parameters. Yeah. I don't want to go in all these details because also I don't know them by heart, and if I need, I take a textbook to look them up. Huh? I don't want you to learn this all by heart. What I want you to is to understand what you do, yeah, to understand what are the influencing parameters of evaporation. The formula then you can look up, and you're all master students in engineering field, so you easily can compute this in Excel or MATLAB or something. Yeah. So, but one I go a bit more in detail, and that's the formula of Penman and Monteith. First, it was the Penman formula. Mr. Penman studied evaporation quite in detail and developed a physical-based method for estimating evaporation of open water. Then, in the 50s of the last century, I think, Mr. Monteith came in and he said, well, actually different plants are also very important. And he further developed the Penman formula by accounting for vegetation characteristics. Nowadays we call that the Penman-Monteith approach or method or formula. Yeah. It's often used to calculate the reference evaporation. It can be used in different climates, different vegetation characteristics. Yeah. This is one everybody needs to know. You don't need to know by heart all the parameters of it, but you need to know what it is for and how it works. It's widely accepted. It's probably it is the most appropriate for different land use because you can account for different land uses. Yeah. Has many parameters. That's a disadvantage. But if you do something physically based, of course, you need many parameters. Yeah. These simpler methods are easier to use, but they don't account for so much variability. Yeah. If you use a formula which only has temperature and humidity, you say basically vegetation doesn't matter, yeah, because you don't account for different vegetation characteristics. A way around this is then to use, for instance, crop factors and modify the calculated evaporation then for different crops with crop factors. This is some examples from the Thornthwaite method. I don't want to go too much into detail on monthly and daily basis of an area in Egypt. You can have up to 5 or almost 6 millimeters per day. That's a lot of evaporation. Here is a comparison of different methods. Haude method is the one that's popular in Germany. Net radiation potential of to Penman method, etc. And you see that the grass reference evaporation has, for instance, 600 millimeters or 596 in this specific city in Germany per year. And you see that different formulas give quite different examples. Huh? So easily plus minus 20–25% even, yeah? Depending on how you look. So you'll be aware of that. This is again then the Penman equation for open water. Again, that's the best method we have. It calculates open water with a couple of constants. The key input parameters are the net radiation, the incoming energy, the water vapor pressure deficit. Yeah, we looked at this one. It says something about how saturated/unsaturated the air is. Yeah, psychrometer constant, and another parameter, the aerodynamic resistance. Yeah, the aerodynamic resistance has the wind speed then as parameter, and the wind speed, the more wind, the more evaporation. We said, huh? Because you have a ventilation always bringing in fresh, new, unsaturated air. So it has the wind speed, energy, temperature, and radiation, yeah, as parameters. Can calculate it like this. And then the Penman-Monteith, so that's the further development of Mr. Monteith who did that. He added two different resistances to account for the vegetation impact. The one is the aerodynamic resistance. You can imagine, depending on the height and the form, the structure of the vegetation, you impact the wind field. Yeah, a little bit of grass, 12 centimeter high, is of course a different aerodynamic resistance than a couple of trees in between, because you have much more turbulence, much more resistance. And the so-called crop resistance. That depends on what kind of crop you have and how that's changed over the different seasons. Yeah. Usually the resistance of grassland, which is kind of a standard grass, has 12 centimeter high grass, well supplied with water, has an crop resistance of 70 seconds per meter, and then different crops have different crop resistances. The Penman-Monteith formula is it's a standard formula which water people use to estimate potential evapotranspiration. If you can parameterize the crop resistance in an actual way, then you can use it also for parameterizing it for actual evaporation, not only potential. Huh? If you know how much water shortage you have or water supply you have, then you can parameterize that in the crop resistance and calculate the actual ET directly. It's a reference ET. Usually you use a 12 centimeter crop height grassland with a crop resistance of 70 seconds per meter and albedo of 0.23, and then you can calculate a reference evaporation for this grassland. Why exactly 12 centimeters? So don't even think about it. It was standardized like this to have a reference to compare with. If you tell me your English grassland in front of your house always is 7 centimeters, that can well be, but this is just a standardization for a reference evaporation, which the meteorological community agreed on. Mm-hmm. Is that clear? Yeah. Basically, you solve this formula. Yeah. But you need a couple of parameters to do so. Let's look at some application of this in a catchment where we worked in the southwest of Germany. We used the Penman-Montes formula. And it's a catchment with quite some mountains, up to 1,500 meters. This is 300 meters. Maybe this is 500 meters. And you see here between 500 and almost 1,500, you have quite some elevation change. You see here the different elevation. And north is here. It's a bit confusing. North is here. So what do you expect now doing at the end of a day? Where do you have the highest evaporation? Where do you have the lowest evaporation? In this mountainous catchment, at the top or in the valley, at the bottom? In the valley, some say. Why in the valley? It's warmer, you could argue. More energy there, more water to evaporate. Some said maybe to the top. What could be the argument for them? Maybe more wind speed up there to bring fresh new wind. Yeah. So it depends a little bit how the meteorological parameters. Yeah. But usually it's much warmer. We said 1 degree per 100 meters if it's the dry adiabatic gradient. So therefore it's 10 degrees warmer down here because it's roughly 1,000 meters deeper. Yeah. Usually higher evaporation in here. And if you look from hour to hour, where would you expect to have the highest evaporation? At noon, 12 o'clock. Where is the highest evaporation in that catchment? What do you think? At the northern exposed slope, southern, eastern, western? What do you think? 12 o'clock, afternoon. Well, the one that are face the sun directly, the one facing the south, because in the south, this is northern hemisphere, noon, the 12 o'clock, noon, the sun comes from the south, and the slopes that are facing the south get the highest evaporation. In the early morning, the one that are facing the east, because that's where the sun rises, the one looking to the west, aspect to the west, the slopes, they have the highest evaporation than in the evening or in the afternoon when the sun is coming from the western side. Yeah? Let's look at that. If that is true, we did some model simulations for that. And you see here, 6 a.m. in the morning, the highest evaporation is here really at the eastern exposed side. This is looking to the east, not necessarily in the valley. The valley has a lot of shadow also. Yeah, 6 a.m. in the morning. There's not so much sunshine coming in. Yeah, relatively low evaporation. But here you have the highest evaporation for the slopes that are exposed toward the sun. 10 a.m. in the morning. Now the highest evaporation is here in the lower part, red, and in the slopes in particular. I need to say that the steep slopes are forested, and the really lower part are grassland. So if you have warmer temperature, exposition to the sun, and forest, that's the highest evaporation. And you can really see that you have quite a distinct pattern from every pixel to every pixel. So we did very detailed Penman-Montes computations here. 2 p.m. Now this is in the morning. This is in the early afternoon. Now not the eastern exposed one, now the one to the southwest. They are now getting most of the sunshine, and there the evaporation is the highest, red colors here. And 6 p.m. in the evening, you really see the one exposed to the west. They get now the direct sunlight, and they have the highest evaporation, according to these Penman-Montes computations. So you have quite a nice pattern from hour to hour how the evaporation is changing during the day. And it's the mixture between the meteorology and the land use parameters. Is that clear? Now we look at annual values. In Germany, we have an evaporation between maybe 400. Oops. 400 and maybe 600, 700. The highest evaporation, the darker, the purple here. Huh? Here in the eastern part of Germany, it's quite hot, relatively dry. You can have potential evaporation up to 600, 700 and above millimeters. Higher mountains, if you would know the topography of Germany, you could say these are mountainous areas. This is higher, and therefore you have much lower evaporation, higher, cooler, less energy available. The Rhine Valley here is the warmest, and then you have more than 650 millimeters of evaporation in this part, and also in the eastern part of Germany. Yeah. We talked about the oasis effect. The drastic one is always when you are in an airplane, you look out of the window and you see these nice irrigation schemes below you, huh? And you see that you really direct, depending on where they irrigate, you have a beautiful, nice cropland, and next to it, sometimes even a desert. Huh? And you can imagine that the water availability in here is, of course, a complete different one than surrounding this. Therefore, you have very large oasis effect here. And depending on where you would measure the water balance and energy balance parameters, here or here, you have a complete different story of evaporation. Huh? I think you agree with me. So it's very difficult from only one measurement then to calculate areal ET. Or deforestation is a big effort, a big thing. This is a picture from Manaus in Brazil, in the tropical rainforest. You see if they cut the forest and use it for rangeland, grassland, pasture land. I mean, it's complete different evaporation behavior than before. So land use changes are of very significant importance. What happens in urban areas when it comes to evaporation? Is it higher or lower? Higher. Okay. But sometimes forest transpires a lot, we said. Huh? Highest transpiration usually you have with eucalyptus trees, which are unfortunately used a lot in semi-arid climates. And but here you can also have high evaporation because of the urban heat island effect, so very high, very hot. But it depends on the availability of moisture, huh? Where and how much you evaporate. Yeah. Or agricultural production, that's a picture from the Netherlands. If you cycle around Delft, you have exactly these type of pictures. If you go to the so-called Westland, where it's full of greenhouses, they are completely regulated when it comes to their climate. So they really optimize the water balance in these greenhouses. And intensive agriculture can also change the evaporation very significantly. Yeah. Good. Let me conclude this evaporation chapter. I think I stressed very clearly, that's my first point, that the water and the energy balance are coupled. Yeah, and the evaporation is the link between the two. Yeah. In the energy balance, we call it latent heat flux. In the water balance, we talk about evaporation. And they are both linked to the evaporation, these two balance equations. Please know the difference between the different processes and variables, which are listed here again, with the total evaporation, soil evaporation, interception evaporation, transpiration, or then another term for the total evaporation is evapotranspiration, ET, reference ET, and the difference between actual and potential ET. Please know that. Use the terminology properly. Don't forget Cinderella, huh? The beautiful girl that nobody sees how beautiful she is. Yeah? That's the effect of interception. So it's an often underestimated process in hydrology. Measurement is usually a headache when it comes to evaporation. Certainly if we want to estimate the evaporation of a whole catchment. The simulations I showed you from hour to hour with the nice evaporation patterns for this catchment in the Black Forest. These are simulations. This is the Penman-Montes formula applied on a pixel and then in a three-dimensional model. Yeah? It's not a measurement. Measuring it at this scale is very, very difficult. Nowadays, with remote sensing techniques, so satellite data, you can estimate the energy balance. And with measuring the energy balance, you can then compute the latent heat flux. But it needs a lot of modeling and simulations. It's not a direct measurement. Huh? It's always some sort of computation. So measuring evaporation is always a headache. We looked at a number of different methods. We said the lysimeter is probably the best one. But it's also very costly to have lysimeters. Huh? or these nice flux towers in the forest. You remember the pictures, also a lot of experimental effort to do that. But that's the only real measurements we can do at the local scale. Yeah. When it comes to computation, Penman or the Penman-Montes equations are the best what we have at the moment. Maybe you develop a new one and it will be then the equation after you name. Let's see. But the Penman-Montes is one. I went a little bit more into detail because that's one everybody should know. Every hydrologist, every water manager has to know this formula because it's probably the best what we have. There are more than 10 others. That are all details on the textbooks. I did not go into details because you can pick it up yourself if you want. But you have to know this one because it's the most frequently applied one when it comes to physical-based computation of evaporation. Aerial estimation, so coming from point scale to aerial estimation is another headache when it comes to evaporation. It's not only a headache when it comes to rainfall. Last day, when was it? Last Friday, we discussed regionalizing rainfall measurements with Thiessen polygons, inverse distance, and all that. The same is difficult when it comes to evaporation because it's not only the spatial regionalization because of distance, it's also the different land use, the different climate parameters that change with topography, with land use, etc. Therefore, regionalizing evaporation is even more difficult. There's a lot of space-time variability, and yeah, it's quite difficult. But we have to do it to do proper land use planning, proper hydrological modeling, etc. Any question on evaporation from your side? Yes, please.
Does the effect of changing topography affect evaporation when it comes to the micro scale? Now, the modeling is on the bigger scale for a real mountain. Let's assume I'm a farmer and I have my ridge is probably typical a particular orientation to the sunlight. How does that affect the evaporation? Because I heard somebody did an experiment now, just changing the ridge angle of the tractor. And produced another result.
Yeah, so also locally you say it can be very variable. Yeah, and I agree. Yeah. So it really depends on land use techniques, plowing techniques, etc. How all evaporation, what you have. And then we try also often to minimize the unproductive soil evaporation, for instance, through different land use techniques. And optimize on the transpiration. But transpiration is plant growth. It's carbon uptake. It's assimilation of carbon. So therefore, you want to store as much as moisture in a semi-arid condition. You want to store as much moisture as you can in the soil and make it for the plants available, that the roots can take it up and take that water. But you want to minimize on the soil evaporation because that's non-productive. That's just evaporating from the soil and not going through a plant, not contributing to plant growth. Yeah. And the land management techniques really have an impact there. Yeah? That's true. Or is that, do I answer your question good enough, or kind of? Well, ask again if I'm, or somebody else has any other question on evaporation? Yes, please.
Also, the season can interact on this evaporation.
Absolutely, it has a very large seasonal dynamic. Yeah? Here we have the highest evaporation, obviously, in the summer. You will experience, hopefully for you, experience some 30 degrees next summer. But now it's 5 degrees outside, sometimes even 0 during the night, so there's very little evaporation at the moment. It's too cold, too little energy income. The trees lost by now most of their leaves, where the water could leave the tree. So now evaporation is very little, less than 1 millimeter per day, often. Yeah? And in the summer, it can be 3-4 millimeters, maybe. Yeah. And a really south-exposed forested hill slope, it can even be more than 5 millimeters, even in this climate. Millimeters a day, it's a lot. That would be very much. For the, yeah. Some computation for my show it can be up to 8 millimeters, but that's really, really very high for this climate. But in tropics, it can be even up to 10 millimeters, which is over then very, very high. So the season matters a lot. I fully agree. Yeah. Other remarks, questions? Yes?
You show us in a picture
show a lot of greenhouse.
Yes.
I just want to know what can be the impact on this measurement on that situation when just we have those a lot of greenhouse.
Yeah. Yeah. Think yourself. Maybe we go back to that picture. Oh.
Yes.
Yeah. So what happens? Rainfall is falling here on the glass roof. What is happening to this water? It's not going down. It does not meet directly any plants. Yeah. It flows on the glass and goes to a drainage system. Yeah. Some of the water is then stored and used for irrigation in the greenhouses. Yeah. And most of the water is discharged away. They only store that water what they need for watering the plants. Yeah. But there's no infiltration to the ground, no groundwater recharge at this situation. Therefore, it's discharged directly and brought to a drainage canal and often to the next river. So this is you make the surface very impervious and produce a lot of direct runoff, but not a lot of soil water storage, infiltration, percolation to the groundwater, and all that. So we produce more direct runoff with these type of structures, and therefore less evaporation. Yeah. But the efficiency, because of the different change in the energy balance of these systems, can be very nice. So you can produce more tomatoes per hectare and higher yields just because of the controlled climatic conditions. Yeah. They even produce. There's more energy coming in than going out. It's a glass house, and the same as the greenhouse effect for the atmosphere. That these things are net energy producers. Nowadays, people try to capture that energy and discharge it back to the grid. That these are little powerhouses. Yeah? You can even produce energy with these things. Not only plants or crops, also small energy producers. Yeah, it's nowadays under development. Yeah?
But we can calculate the evaporation inside.
Yeah. Maybe a nice master thesis for you, huh? Doing a detailed water balance, energy balance in a glass house. Yeah? Yes, we can do that. Yeah. Okay, if that is clear, then we move on. I enter a new topic now. Now we talk about discharge. Yeah? You said precipitation we discussed in detail. Evaporation we discussed some in quite some detail last time and today. And now we go back to the runoff. Discharge. It's globally, it's distributed like this. I think we looked at this figure on during my first lectures. You see a quite heterogeneous pattern. Why do we have so much discharge here in the tropics, humid tropics? Which rainfall mechanism is producing so much discharge? Which rainfall generation mechanism? Frontal rainfall, convection, or what was it again? In the tropics. A lot of convection, and also the ITCZ, the intertropical conversion zone, causes very high rainfall bands here in the humid tropics. Yeah. India, we said, is the World Guinness Book of World Record. They're all found here in the area which is directly exposed to the southwest monsoon in India, where you have a lot of moisture coming here from the warm Indian Ocean, then hitting the mountains here in India, and then producing enormous amounts of rainfall. And you have a similar thing here in what is it, near Ramah, this region here. And this translates, the rainfall pattern translates into a discharge pattern. Of course, we also have different evaporation in the different climatic zones and some DSTT, but this is a long-term average, so the DSTT we can here consider as 0. Why do we have so low precipitation and so almost none runoff in this part, or in this part, or most of Australia, or the Central Asia? These are the subtropical height regions where we have a lot of evaporation, a lot of downward circulation of moisture. You have this Hadley cell we looked at, and this downward movement causes these subtropical dry regions here in the northern hemisphere as well as in the southern hemisphere. And then depending on connection to the sea, connection to mountains, and so on, you have different rainfall patterns in different parts of the world that then also translate into quite a diverse discharge pattern. The objective of this lecture is to discuss discharge measurements. That's where we start now. Then we go into interpreting discharge measurements, so-called the catchment response. Yeah. Then we do something about hydrograph analysis, and finally go to effective precipitation and some simple methods to estimate the peak discharge. Yeah. You do much more about flow and hydraulics and discharge computations during the hydraulic lectures of Professor Meinet, and also I think Dr. Musky and Dr. Brandemati. She's also contributing to that. It's quite a team of going into all the details of hydraulics. I do not do that. I'm also not the most competent person here. The others are more competent than I am when it comes to these things. But I will look at the discharge as a part of the water balance equation during my lectures. How do we measure discharge? Did you do discharge measurements already in the hydraulic lectures? No, not yet. It's very difficult to measure the discharge directly. Huh? This is, for instance, how many cubic meters per second flow through this cross-section here. Huh? To measure that directly is very difficult. Yeah? You will do the details in the hydraulics. So what we do is, we not measure the discharge, we measure the water table, the water level. Yeah? The water level, we measure, for instance, in a recorder, which is in a well, in a stilling well, just next to the river, which we want to measure. And there is a connecting system with a pipe. And these are two communicating vessels. So it means the water level here is the same as the water level there, because they are connected via this pipe. That's clear that these are the same. And here it's much easier to record continuously the water table. We can do that with a float or with a pressure transducer or other instruments. What does it help us to measure the water level? We want to measure the stage as water level, but we want to transfer that to the discharge. To do this, we do that with a so-called rating curve or a stage-discharge relationship. Rating curve is a usually used term. Here you have the water level, and if you have the water level, say, 15 centimeters, this is here, then you have a discharge of 0.05 or so cubic meters per second. Or if you have water level of 30 centimeters or 0.3 meters, then you have a discharge of 0.5 cubic meters per second. Yeah. And this curve here is called the rating curve. If you plot it in log-log scale, very often the rating curve fits along one line, and you can compute the discharge more easily. There are different formula for doing that rating curve. Why do we have different formula to do this? Why is it not always the same? On what does it depend? Yes, it depends, but yeah, it depends on the cross-section, depends on this area here. Yeah. If you have a very flat or more circular shape or rectangular shape or whatever, then we have a different relation between water level, stage, and discharge. Yeah. There are different formula for this. We only look at a few. Having this formula then helps us to compute from the stage hydrograph. This is what we actually measure. The change of water level per time, to change this stage into a discharge hydrograph, which says how much cubic meters per second or volume per time step of the water is discharging through a given cross-section. That's the discharge computation then, yeah. And always against time. And this is a flood event. It starts at 0.1 cubic meters per second, goes up to 1 cubic meter per second, and then you have a falling limb again. So this is a discharge hydrograph of a flood event. I assume everybody has seen something like this before. Good. Maybe that's a good moment to have, again, 15 minutes break. Thank you very much.